Hello everyone, and welcome to Module 3. As you know, we are moving pretty quickly. At least I feel that way. We will be covering Chapter 19. Chapter 19 talks about current, resistance, and direct current circuits. What does that mean? Well, up until now, we have covered Chapter 17 and 18, and 17 or 18 we were talking about the subject of electrostatics, where you have say a charge, and then you have an electric field associated with that charge. We call it electrostatics. The word statics means at rest, not moving, because we dealt with charges that are just sitting there at rest, and then we were calculating, say, the electric field associated with it, or the force between two charges. Now we shift gear, and we talk about something like charges in motion, electrodynamics, okay? Where here you have the charges are actually in motion. What that means is where are they in motion? They are inside a copper wire, so we refer to them as an electric current and so on. So before I talk about the subject, just to let you know, Chapter 19 is a little bit large, but the good news is I am skipping a lot of the sections here. We will only be covering from section 1 until, I'm looking at the hard copy, until section 5. Skip section 6, 7, and until the end of the chapter, which is the last section, is section 10. So we are skipping section 6, 7, 8, 9, and 10. Okay, starting with Kirchhoff rules. So we are only covering, like I said, section 1, 2, 3, 4, and 5. Okay. All right. Let's talk about the subject, and that would make it actually a shorter subject. So hopefully I'll finish this lecture probably in about an hour, or maybe less or something, but around there. So Chapter 19 talks about current and resistance. I'll cover what I will talk about what that means, but let's begin with current. So what is a current? Well, when you think of a water current, which means you have imagine you have a water pipe, and then you have water flowing through it, right? There is the water right here is flowing through it. It's coming out of it in this fashion with a certain velocity. You see what I'm saying? That's called, in fluid dynamics. Similarly, we have something like this. Imagine you get that copper wire that is connected to the outlet, and there is electricity flowing through it. So we have something approximate or similar to it. So here is the copper wire. This is a wire, or sometimes called current carrying conductor. And then you have charges in there, okay, electrons, and those electrons are moving through the copper wire in this fashion, like that, okay? So you get those electrons coming, going through the wire like that. So if you are, let's say, somehow you are able to, this is the cross-section right here, this is the cross-sectional area of the wire. Let's say that with your telescopic eye, or God's eye, if you will, you are able to see the electrons coming out of the cross-sectional area. And let's say you have a timer. So you are counting how many electrons are coming out per second, for example, okay? Or you may want to say how many charges is flowing through the cross-sectional area per second, okay? This flow of charge, which is something like delta Q per delta T per time, is what we refer to it as the electric current I, okay? This I is the electric current. Got that? So what you are observing with your eyes here, telescopic eyes, microscopic eye, those electrons flowing out, and you are counting those electrons, and then you calculate the total charge of those electrons, say per second, as they flow is what we refer to as the current, the electric current. Got that? So that's basically the formal definition of the current. So current is delta Q over delta T. For those of you who are familiar with calculus, the proper definition really is the derivative of the charge with respect to time, but we're not covering calculus here, but that's really the proper way of defining it. Anyway, so that's basically what it is. Now, if you look at the unit, if you ask the question, what is the unit of the electric current? Well, you look at what is it equal to? Well, it's equal to the charge per unit time. So if I put it in bracket to symbolize units, the unit of the charge is the Coulomb, and of course the time is second. So the unit of the current is coulombs per second. Got it? Because it's a flow of charge per second per unit time, so it makes sense. It's coulombs per second. Well, rather than writing it as coulomb per second, which is very proper, very nice unit, we refer to this as, we call it the ampere, or amp. Okay? The formal, the official symbol of the ampere is the capital letter A. Okay? Got it so far? Okay. To give you a feel for this amp, the amp, again, because it is derives from the Coulomb, and we talked about that before, the Coulomb is a very, very large unit, so the amp is also a very, very large unit. To give you a feel for the amp, for example, your electric flashlight, the current through it is something like between 5 and 1 amp, which is really high, actually. For example, the starter in your car. You know what the starter is? You know, when you start the car and you're about to go, what starts the car is a device called the starter. You need to replace it every something like 100,000 miles or so. Especially if you have an old car and you ever replace it, at some point the car will stop working. Not because your battery is bad, it's because you need to replace the starter. It costs about $500, $600, something like that. And that's the starter. Is basically, it gives a lot of charges to the car, to the engine, to get it started. That's the job of the starter. So for a typical car, I'm talking here a small size car like a Honda or a Toyota or something like that, the average current that is given is around 200 amp. For a big truck, I have a Ford F-150. It takes in, I believe, 700 amp. You see what I'm saying? So the bigger the engine, the bigger that. So anyway, that's for a starter. For a typical radio or small television, the amperage, if you will, or the current through going through them is in the order of milliamp, actually pretty, very small. Okay, milli is being 1,000th of an amp, and so on. Okay, let me give you an example and show you how to use this formula, the current, before I move on to something else. And I'm going to go to the book right there. I'm going to go with example, a very simple example, 19.1. Sorry, I'm looking at the hard copy first, so I can tell what page is it. 19.1, page 597. It is right here. Get it bigger. Okay, it says in this example we will relate current to the actual flow of electrons in a real device. One of the circuits in a small portable CD player operates on a current of 2.5 milliamp. Okay, see how tiny it is? How many electrons enter and leave this part of the player in 1 second? Okay? What does that mean? Well, basically what it says, so you have a CD player, and it says that the current through the CD player is 2.5 milliamp. Okay, in other words, the CD player is consuming 2.5 milli coulombs per second of charge. You see what I'm saying? Okay. He says, how many electrons is this? In 1 second. How many electrons flow in 1 second? In other words, here is the wire. Okay, here is the wire that connects to the CD player. The CD player is right here. Okay, and so the electrons are going to the CD player. And again, with my eye, and I'm looking how many electrons are going through the wire to the CD player. You see what I'm saying? Here is the wire. Okay, how many electrons then? Well, okay, let's go back to the definition of the current. We said that the current is equal to Q over T in its simplest way. You can put delta, whatever, but Q over T, right? And that's equal to 2.5 times 10 to the negative 3 amp. Is that right? That is the current right here. So I want to find the charge, the total charge. Well, we know that T is 1 second. That's what he said. He said how much charge is per second for 1 second. Well, the charge of this case, just in this case, it's going to be what? I mean, if I look at the algebra here, it just cross multiply. So Q is equal to I times T. So Q is equal to 2.5 times 10 to the negative 3 times 1 second, right? And that will be equal to That will be equal. So the charge is 2.5 times 10 to the negative 3 Coulomb. Is that right so far? Okay, how many electrons are here? I think we talked about that back in chapter 17. We said that, if you remember, the charge Q is equal to the number of electrons times the fundamental charge. Remember that? So the number of electrons is equal to the charge Q over the fundamental charge. So now, with our situation, so the number of electrons is going to be big Q over the fundamental charge. So that'll be 2.5 times 10 to the negative 3 Coulomb divided by, what's the fundamental charge? 1.602 times 10 to the negative 19 Coulomb. And then we use the calculator to do that. And if you work it out, you will end up getting 1.6 times 10 to the 16 electrons. In other words, what's the meaning of this result? It means, go back to the diagram that I have drawn here. So here I am looking at those electrons coming out of the wire, coming out of the cross-sectional area. And if I am counting how many of them in 1 second, in one single second, there will be, I'm going to count 1.6 times 10 to the 16 electrons coming out of that cross-sectional area. That's the meaning of it. Got it? Okay. That's the first topic that I want to talk about. The second topic, I believe within the same section, no, section 2, resistance and Ohm's law. Okay, Ohm's law, this is a very important law. Ohm's law says that the voltage is equal to the current times the resistance. I'm not going to derive it for you. We just need to accept it, okay? So the voltage is equal to the current times the resistance. Now you may wonder, what is resistance? I'll tell you in a minute. Resistance, okay? This is an empirical law, which means Mr. Ohm, he's a real person, who's the one who discovered this law, and he discovered it not from first principle, like deriving it from theoretical assumption or first principle. He actually figured it out just with practically while working in the lab, working with wires and voltages and so on, and devices and all that, electric devices. And then he discovered this relationship between how voltage, current, and resistors are related to each other, okay? So it's more of a, we call it an empirical law. So V equals IR. What does that mean? Well, first of all, let me tell you what, I mean, we talked about voltage in previous chapter. We talked about, now we just covered current. What is a resistor? Okay, a resistor, think of it like, you know, in mechanics, the friction or the air drag. You know, you have a friction, you know, if you have a, let's say, for example, here is the floor, you have a box here, and you kick the box, what's going to happen? The box is going to move, and then eventually it's going to stop here. What caused it to stop? We say the friction force, okay? So there is a friction force that is always opposing the motion, you see what I'm saying? And that friction force eventually will take over and will cause the box to stop. Similarly, in electricity or electrodynamics, we have something like that. So as the electrons are flowing through the wire, that wire has a certain amount of resistance that resists the flow of those electrons. Do you see what I'm saying? For example, why wood doesn't conduct electricity? Wood or plastic or paper or something like that. The reason is because the resistance inside the wood is extremely large. That's one way to think about it. Okay, where through copper and gold and silver, metals in general, the resistance is much, much lower. You see what I'm saying? So that's one way to think about that. So what does resistance, what I want to do now, I want to find a mathematical way of describing resistance. Okay, so what does resistance depend on? Well, I discover that resistance is proportional to the area, the cross-sectional area. In other words, the bigger the wire, I mean, for example, I have two wires of identical, made from the same material. This wire and say this wire, the same length. The only difference is that the cross-sectional area is different. So which wire would conduct electricity better, the big one or the small one? I hope you will say the big one, because it has like more space for the electrons to flow. You see what I'm saying? So the larger the cross-sectional area, the larger the cross-sectional area, the less the resistance. That's what I'm saying. You see what I'm saying? So in this case, we have the resistance. Sorry, I should have said 1 over A. That's what I wanted to say. So resistance is proportional. It's inversely proportional to the area. Larger area, less resistance. That's what I want to say. Let me write it down again. Larger area result in less resistance. See what I'm saying? However, if I have a wire, let's say the same cross-sectional area, this one and say this one, but the second one is much, much longer. See what I'm saying? And then you have electricity, electrons flowing through both of them. Which one will have more resistance? I hope you will say that one will have more resistance is the longer one, because longer means more resistance, shorter, less resistance. So we can say that resistance is proportional to the length. You see what I'm saying? So in other words here, if I combine those two relationships together, I'm going to say that resistance is proportional to, I'm going to leave a little space here intentionally, is dependent on length over area. Okay? And if I convert this proportionality symbol into equality, so it becomes resistance is equal to a constant multiplied by the length over area. And this constant is actually something that has to do with the property of the material. We call it the resistivity constant, rho L over A. So we come up with this interesting relationship, okay, where such as rho is called the resistivity coefficient. Okay, and you don't need to know anything about it. You can actually look it up in the book. There is a table that you can look up. It's on page 599. Let me show it to you. Here it is right here. See, resistivities at room temperature. So, for example, here you have conductors and insulators. And of course, insulator means very good resistors or bad conductors. And of course, conductors are not very good resistors, but they are good conductors. So, here is the resistivity. As you can see, then the resistivity coefficient here is really tiny. Look at that. For example, for silver, 1.47 times 10 to the negative 8. Okay? And by the way, unit of it is ohm meter. Okay? So anyway, look at that very, very tiny number. Copper, 1.72 negative 8. Gold, 2.44 times 10 to the negative 8. Aluminum, tungsten, steel, they all 10 to the negative 8. Very, very, very tiny. 100 millionths, you know. Lead, mercury, nichrome alloy, and so on, okay? However, for insulators, for example, glass, look at that. It's 10 to the 10, positive exponent. Lucite, 10 to the 13th. Quartz, 10 to the 16th. Very, very large number for resistivity. So the resistivity is extremely large. Wood, 10 to the 8th or through 10 to the 11th, depending on the type of wood. Teflon, 10 to the 13th, and so on. As you can see, the difference between insulators and conductors is huge difference. You see what I'm saying? So we can understand why they are called insulators, because they just do not permit electron to flow through them. Okay? Where here is the total opposite. You see what I'm saying? So these are called resistivity. So when you're working on a problem, you need to come back to this table and to plug in those numbers in there. I would advise you to use this table, not say the internet, because from my experience with resistivity, I've noticed that on the internet or even using a different textbook, they may give you a different number or slightly different, and that will kind of change your answer slightly, especially if you're working on mastering physics assignment. And then you may have done the problem correctly, except that your resistivity coefficient is slightly different. So I would urge you to, the best thing to do, maybe take a screenshot of this table and just keep it on your desktop, so when you're doing a problem, you always come back to it rather than, trying to find it through the book. Just get a screenshot and put it in your desktop. That's just my advice. Anyway, here it is. Let me show you an example and show you how this, tell you how resistivity works. Go through this. Example 19.2, that's kind of a good example. There are at least 2 problems in the homework that has to do with resistivity. I'm going to go over at least one of them with you in this lecture. So let's go to example 19.2, page 601. 601. Right here. Okay, it says, now let's consider resistance of a speaker wire. Suppose you are hooking up a pair of stereo speakers. You happen to have on hand some 20-meter long pieces of 16 gauge copper wire. This is not important, this 16 gauge thing. This is not it's not important for our calculation. It's just a type of wire, electric wires. Okay, but he gives you the diameter. The diameter is 1.3 millimeter. Okay, so we have a 20-meter long copper wire, okay, with diameter, the cross-sectional area, 1.3 millimeter. All right, you use them to connect the speakers to the amplifier. These wires are longer than needed, but you just coil up the excess lengths instead of cutting them. What is the resistance of one of these wires? To improve the performance of the system, you purchase 3-meter long speaker cables that are made of 8-gauge copper wire, 3.3 millimeter. What's the resistance of these wires? All right, basically he wants to know what is the resistance for a 20-meter long copper wire and a 3-meter long copper wire. That's basically what he wants. You see what I'm saying? He babbles too much, I guess. Anyway. All right, let's see how we do this. So first of all, like usual, I'm going to write down what's given to us, and then we'll see how we can solve it. So example 19.2. So we have a copper wires. So the first one is 20 meter, the length of it, that is. And the diameter of it, I'm going to call it 2r, r for radius, right? So it is 1.3 millimeter, and used to connect speakers. Okay, so part A, he says, what is the resistance of the first wire? Okay, now since he mentioned copper, right? So I'm going to go to the table. What is it? Page 599, I think. Maybe I should go this way. One more. And then I have for copper 1.72 times 10 to the negative 8. Do you see that, guys? Okay, so 1.7. So here I have, I'm going to put it here on the side. For copper is 1.72 times 10 to the negative 8 ohm meter. Ohm is the ohm is the unit of resistor. We'll talk about it in a second. Okay, this is the unit, after Ohm's law, Mr. Ohm, so we call it ohm meter. Okay, so we know that the resistor R is equal to what? Rho L over A, and we have everything. So 1.72 times 10 to the negative 8, this is the rho. L, he said, is 20 meters, divided by A is what? The cross-sectional area, not the whole area of the wire. It's just the cross-sectional area, which is basically a circle. You see what I'm saying? Here is the wire, just for those of you who are a little vague on it. Here is the wire. Assume it's very long, 20 meters long, right? 20 yards. So this area right here is what we refer to as A, the cross-sectional area right here. And as you can see, oops, I reached the edge of the screen. And that's, lower it. So this A, it's basically pi r squared, right? Just the area of the circle. So that would be pi r squared, and that would be pi r squared. Now what is r? Well, we said that 2r is that. So in this case, r is equal to 1.3 times 10 to the negative 3 meters over 2. And let me use my calculator for that. So I have here 1.3 negative 3 divided by 2. Answer, the radius 6.5 negative 4. So the 6.5 times 10 to the negative 4 is r squared here. And then I go back and plug it back into the formula. This formula. This one, if you will. So that's going to be r equal to 1.72 times 10 to the negative 8 times 20 meters. Pi is 3.14, of course. 6.5 times 10 to the negative 4 squared, and then you calculate all of that. And when you do, I'm just going to get the answer from the book. There's no need to. I hope we did it the same way I did. So there we go. So yeah, we did the same thing here, and the answer is 0.26. So it will be 0.26 ohm. There we go. Now we do the same thing for a 3 meter wire, exactly the same thing. So here we have R equals rho L over A, and then the only difference is that the area, or the diameter rather, is not 1.3, it's something else. It is 3.3. You see that? And then we do the same thing. And when you do it, here we go, here's the answer. You just basically plug the same thing. Also, the length, of course, is 3 meters. No, it's not 20 meters. And then you plug it in, and you will end up getting, as you can see here, is much smaller than you see. Look at the resistance here, 6 times 10 to the negative 3, where for the 20 meter wire, it is 0.26. So as you can see here, the resistance in the 20 meter is larger. Why? Because the length is longer, which one is much less because it's a shorter wire. You see what I'm saying? So he said the shorter, fatter wires offer 40 times less resistance than the longer, skinnier ones. The lower the resistance, the higher the current flowing through the speakers. Got it? Okay. All right, just a simple example. Let me do one more example. I think I'll let you work on 19.3. I think I want to move on to the next topic. I do have several examples on resistivity. At least I'm going to do one or two from the homework problems. I mean, in this book, he relates resistivity with temperature here, how resistance affects it, but I'm not going to be covering that. You can read about it, but I don't think there is any homework problem on this one, on this topic. Okay? All right. The next topic is electromotive force and internal resistance. Let me talk about that, this section here. The subject of this is internal resistance. Okay, before I talk about it, let me just review. I want to make sure that we have covered the topics that I wanted to cover here, and that is, okay, we said Ohm's law is equal to IR, right? We said that the unit of the resistance, the unit of it is the ohm, right? The unit of it, I'll put it in bracket like that. And we said that the current is equal to the charge per time. Okay, these are the formulas that we have covered so far. Keep those in mind. And I don't think I've given you any example on Ohm's law here, but we will talk about that, I promise. All right, now internal resistance. What does that mean? Okay, let's say, for example, you buy a brand new battery. Let's say a battery for your calculator, say a AAA. So here is the battery that you buy. That looks typical looking battery. Let's say a AAA. It looks something like that, where this is the positive electrode and this is the negative electrode here. Okay, now if you put a voltmeter across it, okay, I don't know if you know that or not, but the voltage across a AA or AAA batteries is basically 1.5 volt. Okay, you can look it up. You can just look at the battery. You'll see the number right there. I believe it is close to the positive terminal. You'll see 1.5 volt. Okay, that's for the fresh, brand new battery you just bought. Now, if you put this battery inside your calculator or your flashlight or whatever, and you use it for a while, say a month or so, you take it out and then you put the voltmeter across it, you'll discover it is, because it's gotten weaker, you know, or what we call in daily language, less juice in it. So now it is, say, 1.3 volt. So what happened to the 0.2 volt? Okay, what happened to it? Is it gone? Okay, here's what happens. Okay, so you have here the current. Here's the battery, our battery here, and the current is flowing through it. Here's the battery, and the current is flowing through the battery, something like that. Think of it like it's going like that. There's the electrons going through it. Okay, now inside the battery, it's made out of certain material. Okay, certain, if you will, electrochemical material. Okay, those electrochemical material over time, okay, they would start decaying or corrode. As a result of that, those electrochemical material will not be conducting electricity or will not be allowing the electron to flow as smoothly as before. You see what I'm saying? So as a result of that, the resistance of those electrochemical material, because they are corroding gradually, the resistance will increase. Or in other words, the internal resistance of the battery will actually increase. So now you're not getting any more 1.5 volt, but you're getting a little bit less. And if you even use it more and more and more, it's going to be 1.1 and then 0.9 and so on. It may go to 0 even. Okay? And of course, your device will stop working maybe at 1.3 already. And we'll just, because the device, your device, say your calculator, is designed to work at a minimum of 1.4 volt, for example. I don't know what it is, but let's say that. Below that, it's not going to work. So that's basically what happens. So over time, batteries or something like that, or anything that is that produces electricity, over time, those electrochemicals inside of it will decay, corrode, and as a result of that, it will not be conducting electricity as good, and as a result of that, the internal resistance of it will drop down, will decrease. Okay? So that's basically the story. So we have something called, now what does that mean? Okay, so we have something called the electromotive force. Electromotive. It's an old term that goes back to the 19th century. Force, and it has nothing to do with force. Okay, but that's an old term for voltage. This is what they called voltage back in the 19th century, or even probably before that. The electromotive force, and this name kind of stuck. And for short, electromotive force, we call it the EMF. Okay, so when you hear or read EMF, your book uses EMF in small letters, EMF like that, as a word, and it's almost a word. The EMF is basically, we mean the voltage. So if you're confused, just replace that word, EMF or electromotive force, with the voltage. You got that? So we have something like this. When I first bought the battery, and I measured what's the voltage across it, just like I did here, what I have measured is the EMF. Oh, the symbol of the EMF, sorry, is kind of a cursive letter E. Okay, it's not the block E for electric field or total energy, whatever. It is the cursive letter E like that. So this is the EMF, or sometimes we refer to it the source EMF. So over time, what happened is that the internal resistance inside the battery have increased. As a result of that, when you measure the voltage across, is what we call the terminal voltage. So this is the electromotive force, EMF, and then we have what is called the terminal voltage. Terminal voltage. What is the terminal voltage? It's basically what the voltage that you measure with your voltmeter. Okay, so what is terminal? What you measure with a voltmeter. Okay, in other words, if you take that voltmeter and put it across your fresh battery, it's going to read 1.5. After a while, it's going to read 1.3, for example. Okay, and after a while, it's going to read 1.1, and so on, right? So it will keep dropping down. So that's all of these measurements are all terminal voltages because you're using a voltmeter to measure. So the difference between the EMF, which is for like the brand new ideal battery, there was zero internal resistance. Okay, so the difference between them, terminal voltage V sub T, I forgot to mention that, will give you the internal resistance, but we're going to write the internal resistance as this, I small letter r. Remember Ohm's law? It's I big R for the resistance, but because it's internal resistance, we refer to it as I with small letter r, where small letter r is the internal resistance. Okay? So the EMF is basically, if I'm using this formula, is equal to the terminal voltage plus IR. That's an important formula that we need to deal with. I'll give you an example. Looking for an example from my notes here. Oh yeah, example 19.5. And we have, I think, at least one or maybe a couple of problems from the homework. I'll try and do one of them in this lecture. 19.5. Let me go to the book. 19.5, let me locate it first. Sorry, there it is. Page 604. there we go. Here's what I told you about. Here is the internal resistance. This is the EMF, and this is IR, the internal resistance times the current, and this is the terminal voltage. He called it A and B, AB, V sub AB. I like to call it V sub. I think he called it V sub T somewhere. I hope, maybe not. But anyway, V sub AB is basically what I call the terminal voltage. And so then, of course, if you solve for I, the current will be the EMF divided by big R, the resistance of the wire, which you can measure from that formula, the resistivity formula we dealt with, plus the internal resistance. Usually the internal resistance is given to you, or maybe you're asked to calculate it. Anyway, so there we go. Let's look at this example. He said, in this example, we will see how internal resistance affects the performance of a battery. As a flashlight battery, or a car battery for that matter, ages, its EMF stays approximately constant. Remember I told you EMF stays constant. EMF is basically the ideal battery, the one when you just bought the battery, it's fresh battery, that voltage that you measure there is really the EMF, and you can just keep it there. And as time goes by, the battery's voltage drops down, and because of the internal resistance. Anyway, okay, a fresh battery has an EMF of 1.5 volt, got it? And negligible internal resistance. When the battery needs replacement, its EMF is still 1.5, but its internal resistance has increased to 1000 ohm. This is the little r. You see what I'm saying? This is the little r right there. Okay, if this old battery is supplying 1 milliamp, this is I, 1 milliamp to the light bulb, what is the terminal voltage? I hope you think it's a simple problem. I don't think it's a difficult one. All right, so let's write down what's given to us. So he says the EMF, he actually admits, says this is the EMF, is 1.5 volt. And he said the current in the battery is, what is it, 1 point something? 1 milliamp right there. So that will be 10 to the negative 3 amp. That's the current. And then the internal resistance, small r, is 1000 ohm. Okay. What else? And then he's asking for the terminal voltage. Okay. So what did we say? We said that the terminal voltage, or let's start with the EMF. So we said that the EMF, here it is right there. This is the formula right here that I'm talking about right there. So the EMF is equal to the terminal voltage plus I small r. Of course, he's asking for the terminal voltage, so I'm going to solve for it. So terminal voltage is equal to EMF minus IR. You see that, guys? And then I just plug it in. So I have the EMF is 1.5 minus I is equal to 10 to the negative 3 amp times the internal, which is 1000. As you can see here, 1.5 minus what? Minus 1, correct? Because this is minus 3 here, and this is positive 3, so it becomes 1. So basically, it's the terminal voltage is half volt. What does that mean? It means that if I bring my voltmeter and go to this battery, remember I bought it fresh, and the EMF on it, when I first bought it and I first measured it when it's brand new, it was 1.5. So after a while, now when I measure it, it's reading 0.5. Why? Because it has too much internal resistance. Because what makes that battery, those material that makes the battery have corroded or decayed, and as a result of that, it's not flowing electricity as smoothly. So that means the internal resistance have increased. That's the whole idea behind that. Okay? Okay, good. All right, one more topic. These are really small topics, as you can see, and I hope you don't think they're hard. Kind of an easy chapter, in my opinion. You may disagree, but I think it is. All right, another topic, it's power and energy. What chapter is 19.4? Let me just go to it, just make sure this is the title. power. I'm looking at the hard copy. It's easy to flip pages. Yeah, so it is page 606. Right here. Okay. It's kind of a short short section, but I'll go over it quickly. Okay, remember, before I talk about it, remember what's the definition of power? If you remember from your 151. Well, power is equal to work over time. Right? In general, power is really energy over time. That's really what it is. And so it's energy, any kind of energy, even thermal energy, any kind of power. I mean, of course, we're concentrating on electric power, but there is all kind of different power, mechanical power, or heat, thermal power, and so on. So, but energy, of course, if you look at it in terms of unit, well, energy is joule, time is second, so it is joule per second. And this joule per second, we refer to it as the watt, or capital W. Okay, let me give you an example. You go to the store, to Walmart, and you buy a light bulb. Okay, and let's say, what's the favorite light bulb? Let's say 40 watt. Okay, it's not as bright as say 100 or 75, but let's say you buy it, 40 watt. What does that mean? What does that mean when we say, I bought a 40 watt light bulb? What does that mean? It means that this light bulb, when it is on, it is 40 watts. It's consuming 40 joules of energy every second. That's the meaning of it. Okay? Where, say, a 75 watt, it's consuming 75 joules of energy every second, and so on. You got that? That's basically what it is. All right. Let me go back to the power. Again, we are concentrating on electric power, not thermal power or mechanical power. So here the power, which is big P, is equal to energy. Again, I like to call it energy rather than work. Both the same thing. I mean, work and energy are the same. Divided by time. Well, we said that energy, if you remember, well, okay, work is force times distance, correct? Again, from 151, mechanics. And the force, when we talk about here Coulomb's law, it is QE. We covered that last chapter. QE times D. Well, what is ED? That's the voltage, if you remember. So it is Q times delta V. So that will be work, or, again, energy. So now if I go back to power, and it says it is energy over time, I can plug this thing in there. So it becomes Q delta V over T. Is that okay, guys? Now, what is Q over T? Go back to the very first page. If I can go there. There it is. Right here. We said the current is Q over T. Aha. So here we have Q over T here. So the power is equal to the current times delta V. Or for simplicity, power is equal to IV. Remember, Ohm's law says what? V equals I. Oops, sorry. It's equal to V equals IR. Right? So I can use this to plug it in there, because now I know that power is equal to IV, okay, which is a very cool relationship. And I can use V to be IR, so in this case power is equal to I squared R, okay? And if I want to eliminate, say, I, see if I have, here I have, let's say I is equal to V over R, and then I take this and plug it back in here, so that will be power is equal to V squared over R. And I get those famous three relationships. This one here, and this one here, okay, for the power. They're all equivalent because you're using Ohm's law. So power is equal to IV or I squared R, depending on what you have, and power equal to V squared over R. Again, it depends on what variables we have. Got it? Okay. Let me show you how this works. Let's do example 19.8. I promise we'll do some problems on the homework, but I'm just trying to explain the lessons for you. 19.8. It's right here, page 608. There we go. It says, let's look at a simple example of power delivered to a resistor. Okay. Now, when we say a resistor, by the way, I mean, we talked about resistors. The ideal resistor, or a resistor that is you see all the time in your daily life, anything that resists the flow of electricity is a resistor. The ideal one would be like a light bulb. Why does the light bulb lights? Well, it's because it resists the flow of electricity in the tungsten wire, and as a result of that, the tungsten wire heats up because it's resisted. And then that heat, it heats so much it glows, well, light. See what I'm saying? So when you read the word resistor, what is it in you? How do you visualize a resistor in our daily life? The light bulb. Or if you have an electric stove in your apartment, your kitchen, that's a resistor. When you turn it on, that coil thing, and it turns red. Why does it turn red? Because it's a bad conductor. It's made out of a material. I don't know. I'm not sure what material is it, but it's a bad conductor. It's made out of a material that resists the flow of electricity, the voltage, and as a result of that, it keeps it in there. And of course, that's energy, electric energy, and it heats up so much it glows and it gives off heat to whatever you're cooking. Same thing with space heater. When you have a heater, with air, but why is it hot? Well, there is a coil in there, something similar to the tungsten. I'm not sure what kind of wire, but again, that wire, it resists the flow of electricity and it heats up, and so on. Okay, so these are all examples of resistors. All right, here we have the bulb of an interior light in a car is rated as 15 watt. Okay, so the wattage on the light, like say the dome light in your car, is 15 watts. And operates from a car battery voltage of 12.6 volt. What is the resistance of the light bulb? Kind of an easy problem. All right, so here you have a light bulb. The power on the light bulb is 15 watt, he said, and what always write down was given, even if it's an easy problem. The voltage is 12.6, so the voltage is 12.6 volt. What else do we have? Oh, that's it. Okay, and then what is the resistance of that light bulb? Okay, so again, we pick whichever of the three that we have here. Whoops, one more. There we go. We can pick this one, or this one, and depends on what we have. We are given. We're given power. We're given V. He wants R. So I would go with this one. You agree with me on that? So we have here power equals V squared over R, and therefore R is equal to V squared over power, and that's it. So it becomes 12.6 squared divided by the power is 15 watt, and then we just calculate that, and there we go, and you'll get 10.6 ohm. So that's the resistance of that light bulb that he's talking about. Simple? Okay. One more topic, and then we are basically done with the chapter. Then we'll do some problems from the back of the chapter. Okay, the last topic is arrangement of resistors, series and parallel. Just like we did in the last chapter, we covered how to arrange capacitors in series and parallel, and there were some formulas associated with each arrangement. So we have similar situation for resistors. Again, when we talk about resistor, think of it like light bulbs arranged in series and parallel. So let me go over resistors, go over the formulas. I'm going to write them down. Please take notes on those formulas, and then I will do some example, maybe one or two examples on that. So we have two arrangements here, series and parallel. We'll start with a series. I'm going to be simple on this, so just going to imagine you have two resistors, and then I have a power source, EMF, the battery power source. I'm going to call that R1, and this is R2, and this is the EMF. I can call it E, or I can call it V, whatever you want to call it. We'll call it V. I think your book uses V. Yeah, it uses V. All right, and so if I have this arrangement, I can create an equivalent resistor, excuse me, an equivalent circuit to it. So I have one equivalent resistor. I'm going to call it R sub EQ, and then my old battery, the same battery. How did I arrive at this equivalent resistor? It's simply you add up, or you take the sum of all the resistors that are in series. So just basically R1 plus R2 plus R3 and R4 if there are more resistors. Okay. The voltage, well, hold on. So here we have, let me go back to the original circuit. So here we have also a current. We didn't have a current in the capacitors. Here's the current right here. And this current, use my mouse so you can see it. So here is the current. It goes through the first resistor and then through the second resistor. And nothing happens to the current. The current will stay the same. In other words, the current through resistor 1 and the current through resistor 2 is basically the same current as the one that comes out of the battery. Okay? In other words, I is equal to I1 is equal to I2. Okay? However, the voltage here is different than the voltage across the battery, that is. It's different from the voltage across R2 and it's R1, and it's different from the voltage across R2. Okay? So here we have the voltages are different, but they sum up to the original voltage. So it's V1 plus V2. These are the three formulas for the series arrangement. Okay? So let's review. The equivalent resistor, simply add up the resistors together. The current through the series arrangement are the same, the current. And then the last thing is that the voltages through across each resistor, when you sum them up together, you come up with the voltage across the EMF, the source. Got that? Okay. For parallel, for the parallel arrangement, I'm going to draw the same circuit, except it's in parallel situation, like that. And here is my EMF, regardless of the, let me use the same polarity, like that. And that is the EMF. And then, of course, we have a current. And by the way, I keep forgetting, the current flow always goes from the negative to the positive. And maybe I forgot to mention what the battery looks like. This is a battery. I forgot to mention that. I'm sorry. Here is a battery. This is the symbol of the battery. And the short segment, this one, is a minus, and the longer one is positive. It's always. And then the current always goes from negative to positive. So now the current direction would be this way. Be careful that you must know the direction of the current by looking at the battery. So in other words, if I have a battery that looks like that, then the current is this way. If the battery looks like this, then the current going this way, and so on. Get that? Okay. All right, so I'm going to call this R1, and this is R2. And in this case, the equivalent resistor, now, okay, well, here is the when I draw it in one single equivalent resistor, here's my old battery, here's my voltage, this is Req, and the equivalent resistor, you can get it by the following. 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3 and so on. We only have 2 here, okay? One thing that is interesting about that is that it's unlike the current arrangement here. See, if you follow, here's the current right here, right? As the current goes through, look what will happen when it reaches this junction. It's going to split. See that? Think of it like a water pipe. Okay, let's say that, imagine this battery represents a water pump, and then the wire here represents a pipe, and then the water is flowing through it. When it reaches this junction, it will not be necessarily true that I1 and I2 are the same. Maybe not, okay? So, however, I1 plus I2 should equal to I. So if this is I right here, that's I, and this is I1, and this is I2, what will happen is that I is equal to I1 plus I2. Make sense? Okay, so basically you sum the current to get the original current. However, the voltage across the battery here is the same as the voltage across the resistor 1, and it's also equal to the voltage across resistor 2. So here we have V is equal to V1. It's also equal to V2, okay? And so these are the 3 laws for the parallel arrangement. Got it? Okay, let me give you an example. Simple example. The best example is, I'm seeing it in the book here, example 19.9. Let me find it in the book. It's page 611. There we go. He talks about resistors in series and parallel. It's basically what I have just said. And then we have this circuit right here. Do you see that? I'm going to do this problem right here. So he says, in this example, we will use the constant of equivalence resistance to determine the current in the circuit. 3 identical resistors with resistances of 6 ohm. So each of them is 6 ohm. R1, R2, R3. To a battery with an EMF of 18 volt. Where is the battery? Right here. There's the battery. Of course, the current is going to go this way, right? Because that's a short segment. Long segment is going to go this way. And the voltage across is equal to 18 volt. 0 internal resistance. He asked, find the equivalent resistance, and find the current in each resistor. Got it? Okay. Let's work on it. There is a homework problem similar to this example. I think it's number 46 or something like that. Anyway. Example 19.9. So what I have in here, let me put it on the side without leaving the screen. There. So what I have in here, here's the battery. Here is the first resistor. And then I have 2 resistors that are in parallel with each other like that. Okay? And then go back to the battery like this. The voltage here, the EMF V, is equal to 18 volts. And of course the current going this way, this is 6 ohm, 6 ohm, 6 ohm, and he's calling this R1, and the upper one is R2, and the lower one is R3. And we want to find the first thing, always when you see a circuit like that, the first thing you need to do, just like we did in the previous chapter, find the equivalent resistor. Got it? Or resistance, okay? Just like we did in the previous chapter, you find the equivalent capacitance. Okay? We're going to do the same thing. All right. So how do we do it? We work on it slowly, step by step. Let me work on it vertically like this. So the first step I do is that I want to get the equivalent resistance between R2 and R3. Okay? And remember, these are in parallel. What that means, I'm going to use this formula, because this formula, see that, in parallel right here? So it is 1 over R1 plus 1 over R2. So I'm going to do that. So what I'm going to do, so first thing you do, you basically redraw the same circuit. So you won't make any mistake. Here's my battery. Here is the equivalent resistor only between 2 and 3, okay? And then here is the old R1. So I'm going to keep R1 there. I'll come back to it later. 6. And this is 18 volt right here. And now I'm asking the question, what is the equivalent resistor here? Well, the equivalent, I'm going to write it on the side here. It basically, since this is 6 ohm and this is 6 ohm, so basically the equivalent is 1 over R equivalent is 1 over 6 plus 1 over 6. You see what I'm saying? So when I add them up together, it's going to be 2 over 6, 2 over 6, excuse me. And that's 1/3, right? 1 over R EQ. So therefore, R EQ for this one is 3 ohm. So basically this one is 3 ohm. Okay? The next step, I'm going to redraw this again. Again, I'm working vertically. So now I'm going to combine those two together. Well, they are in series, which means what? I can just add them up to get directly. So my new circuit's going to look something like that. Just one single resistor. I'm going to call it REQ. Just to distinguish this REQ from this, can I just go back to this one and call it prime maybe? I mean, I don't think it's important, but anyway. So basically it's going to be REQ for this situation is going to be 3 plus 6, and that will be 9 ohms. So the equivalent here would be 9 ohms. Okay? And of course this one is 18 volt. Got it so far? Okay. And of course we have the current going like that. Here is the current, and the current goes through the circuit. Now I want to find the current. Well, how do I find it? Well, Ohm's law. V equals IR equivalent. So I is equal to V over R equivalent. And of course voltage is 18 volt divided by 9, and that'll give me 2 amp, right? So here I have the current is 2 amp. Now, he's asking for what is the current through every single resistor here, all of them, through R2, R3, and R1, okay? What I want to do, the best way to do it is you actually work backwards. So you start from the original, from what you, the last step here, and then you work upward, backward. I'm going to change the color just for the sake of clarifying things. So I'm going to put red, and I'm going to work backwards. So we start from here. We said that the current here, this current right here, is equal to 2 amp, right? We got it to be 2 amp right there, guys. Is that right? Now I'm going to work backwards. So now I'm going to look at this circuit right here. Now this circuit, those two resistors are in series. What does that mean? We'll go back to the formulas. If they are in series, the currents are equal. See that? So what does that mean? It means if this current is 2 amp, then those two currents, the current going through those two must be also 2 amp. So the current I1, I can just say, is 2 amp, and this current right here is also 2 amp. You see what I'm saying? I can also find the voltage across that, but I'll do it in a minute. Okay? Now let's go backwards again. Now, so now I know the current through R1 is equal to 2 amp, which makes this R1 is basically 2 amp. Now I need to work on what is the current here and here. You see what I'm saying? Well, what is it? Well, these are in parallel and currents are not equal in parallel. But what's equal in parallel? The voltage. So what does that mean? Well, I go back to my original, the resistor that I got from here. And what is the voltage here? Well, the voltage is just IR, right? Ohm's law. So that will be 2 amp times 3. So the voltage here is 6 volt. You got that? So the voltage across this 3 ohm resistor is 6 volt. What does that mean? It means if I go backwards, the voltage here and here must also be 6 volt. Why? Because the rule said that. Here, look, if they are in parallel, the voltages are equal. So now the voltage here is going to be 6 volt, and the voltage here is 6 volt. Is it 6 volt? I forgot. Yes, it is, right here. 6 volt. So now, if I know the voltage is 6 volt, and I know the resistor is 6, and this is 6, so that means I can use Ohm's law again. V equals IR, and therefore I is V over R. So that will be 6 over 6, and that's 1 ohm. Excuse me, 1 amp. So the current through here is 1 amp. Got it? Make sense? Same thing. I am going to use the same logic for this one here. So I is equal to V over R, and that will be 6 over 6, or what I'm trying to do is here, R2, right? And this one is R3. And that will be equal to 1 amp as well. You got that? And there we go. We are basically done with this. He said in the circuit, he said find the resistors, excuse me, the current through every single resistor. We found it. So the current through the R1 resistor is 2 amp, and the current through R2 is 1 amp, and the current through R3 is also 1 amp. And there we go. You got it? Okay. That's about it for this lecture, and for the rest of the time, I am going to be spending it. Maybe I'll do a couple of problems from the homework. Let me go back to black color. I think I picked, let me see. Give me a second. Look at the problems. I'm going to do number 22. Let's start with 22. 22, for some reason, mastering classifies it as difficulty 5. I don't know why. In the book, it's level 2, but in mastering is classified as difficulty 5, which is like maximum. I don't know. I don't see it as a difficult problem. That's one reason why I want to do it. So let's do it. It's on page 627. And like I said, the rest of the sections are skipped. Kirchhoff law and RC circuit, we're just going to skip them. This is basically what you need to study for homework and for the midterm exam. Anyway, 627, excuse me. Number 22 right here. It says a steel wire. Oh, I remember this one. Yeah, it is kind of toughy. A steel wire of length L and diameter D has a resistance of 100 ohm. Okay? What current would flow through a silver wire of the same diameter and the same length if 10 volt potential difference were applied across its length? Kind of a tricky problem. Okay? Let's talk about it. All right. Let me read it again. I like to draw or draw a free body diagram and write down what's given. So we start with a steel. He said he has a steel wire, and then he has a silver wire. Okay, the two different ones. I want to find what's the relationship between them. He said a steel wire, the length of this wire is L and diameter is D. All right, so the length is L and the diameter is D. has a resistance of 100, and the resistance of the steel wire is 100 ohm. Okay. Now, period. Then he goes to the next sentence. What current? He's asking for a current on the silver wire. What current would flow through a silver wire of the same diameter? So it has the same diameter. So the same D, okay? What am I? And the same length, okay, also the same length. If the potential, so it has a potential V equal 10 volt potential difference across, potential difference where applied across its length. So he says the voltage here is 100 or 10, I'm sorry, 10, sorry. So we have 10 volts. Okay, and he's asking for what is the current through it. Okay, how do we do this problem? Well, because here he's giving you two wires, one steel, one silver. They're both different. Okay, similar in terms of geometry, the length and the diameter. So it has the same cross-sectional area and the same length. So you get the same thing. Of course, you're going to have different resistance for both of them because they're different material. And then you have a voltage across. As a result of that, you have so what would be the current? Okay, so what you want to do is you want to find a link between them. Okay, this link, well, we have a link between them. Either they have the same length and they have the same D, the diameter, whichever you want. Let's look at L. So we said that, he said that, it's given to me, that L for steel, I'm going to call it ST, is equal to the length for silver, SL. Okay, so far? Okay. Now, this is how I begin the problem. I'm basically showing you how I am thinking about the problem and how to solve it. Okay. Now, that's one thing. The second thing is, I know that the formula R equals rho L over A. A being what? The cross-sectional area. So R, the resistance, is equal to rho L over pi R squared. I'm going to use small letter r for radius. I don't want to use big R because the big R is resistance. So that's the formula that I am familiar with. So if I solve for L here, so it's going to look something like that. Pi R squared, big R, over rho. You see that? So I can take this formula and plug it here. Got it? So in this case, for steel, it's going to look something like that. Pi R squared times the resistance over rho. Now, of course, the rho here is the resistivity for what? For steel. Got it? Okay. And that's for steel as well. Of course, he said the diameter is the same, so logically the radii will be the same. So I don't need to put any symbol underneath it. For silver, I'm going to do the same thing. Pi R squared, the resistance for silver over rho, the resistivity for silver. So far, so good? Okay. Now, since they have the same diameter or the same radius, so this R and this R the same, pi the same, so they can just cancel out happily like that. You agree with me on that? So I'm left with R steel over rho steel, which I can look up in the table, equal R silver over rho silver. Again, I can look it up in the table. What else is given to me? Well, he gives me the the resistance right here of the steel. So this R really is just ST here. So I can plug it back in there, this ST right here, guys, right there. So I can substitute 100 for it over resistivity ST equals to RSL over resistivity SL. Got it so far? Remember, RSL and rho SL and rho ST I can look up in the table for resistivity. Now, what about this one? RSL, the resistance of the silver. I don't know it. He didn't give it to me. But he gives me V and he's asking for I. What does that mean? Well, I go back to Ohm's law. V equals IR. So R is equal to V over I. So I can take this and plug it right here. See what I'm saying? See how I did this problem? So I have here 100 over rho ST equals to V over I rho SL. Of course, this V is what? Is 10. It gives it to me right there. See that? So in this case, I would have 100 over rho ST equals to 10 over I times rho SL. I'll keep going vertically like that. And I am interested in what? I'm interested in solving for the current, because that's what he's asking for. See that? Oops. Right there. And I'm basically done with the problem. All you need is just plug in your numbers. So now if I do cross multiplication, let me go slowly. So I have 10 rho steel equals 100 I rho silver. I should have reduced 100 and a 10, but that's okay. And then in this case, I would have I, the current, I'm going to solve for it, is going to be 10 rho steel over 100 rho silver. And of course, 10 over 100, that'll be 10. So that's going to be rho steel over 10 rho silver. And then all I need to do is just to plug in the value for steel and silver. Let's do it. So if I go back to the table, I forgot which page. Let me go back in my hard copy and find it. It's in the beginning of the book, page 599. So I'm going to go to 599. 599. Right there. Silver, 1.47 times 10 to the negative 8. And then steel is right here, 20 times 10 to the negative 8. So here I have, for steel is 20 times 10 to the negative 8 divided by 10 times silver, 1.47 times 10 to the negative 8. And before I use my calculator, I can be smart about it. Those will cancel out. 20 divided by 10 is 2. So basically, I'm going to get 2 divided by 1.47. And then you just get that answer. And that will be 2 divided, I'm using my calculator here, 1.47. Answer, 1.36. So the current here will be equal to, my pen doesn't want to erase, there we go. It's 1.36. I hope I did it right. And there we go. We got the current. Got it, guys? Okay. Maybe one more. I don't know which one. 28. Let me see if 28. Yeah, let me do 28. It's easy homework. I hope it is. It's not very. Oh, that is 35. The eel. I don't know if it's homework. Yeah, the eel problem. The eel looks kind of easy. Let me do. I'll do 28. How about that? Eel. The number 35 is kind of easy. I'll do 28. It's have to do with internal resistance. Since I promised I'm going to do one of them. Number 28. And then we'll call it a day. We'll call it a lecture. I thought I'm gonna finish this lecture in 40 minutes or so, or 50 minutes, and I'm already on almost an hour and a half. But that's okay. I hope you're benefiting from it. That's what counts. All right, number 28, on page 627. 627. Right there with this diagram right here, it's has to do with internal resistance. It says here, consider the circuit shown in the figure, which is right there. As you can see, we have a resistor. This is a battery. This yellow thing is in a battery, and this resistor inside is the internal resistor. Remember, there is no actual resistance there. It's just the corrosion of the material created a resistance. So to symbolize it, we actually draw the zigzag line to symbolize that internal resistance. And the 24, I believe it's probably the EMF. And of course, we have a current here is 4 amp. Okay, you see that? So you have a battery. Think of the resistor here is basically the light bulb. So you have the battery connected to a light bulb. The light bulb is lit. And let's assume that it's lit for days and days and days non-stop. There is no switch there. Eventually, what's going to happen? The light bulb will start getting dimmer and dimmer. Why is it getting dimmer? Because the internal resistance R is increasing. Or the battery, the material of the battery inside is decaying slowly. So when something decays, its internal resistance increases. That's basically what it is. Okay? So that's basically the story. Okay. So he said, consider the circuit shown. The terminal voltage is 24. Oh, okay, so this is not the EMF. So this is the terminal voltage 24. I'm sorry. I've read it wrong. The terminal voltage of the 24-volt battery is 21.2. I should have read it that way. So the 24 here is the EMF, and the terminal voltage is 21.2. The terminal is always less than the EMF. Remember that, and I hope it makes sense to you, right? So let's write this stuff down. So here we have the EMF, E, the cursive E, is 24 volt, and the terminal voltage V sub T, again, your book calls it VAB or something like that, 21.2 volt. Okay, and then we have a current. Just by looking at the circuit, it says 4 amp. What is the internal resistance small r of the battery, and what is R? So basically he's asking for what is find R, and B, find capital R. Okay, simple. I hope it is. So how do we do it? Well, we go back to the same formula. It says that the EMF is the terminal plus IR. Remember? That's the big famous formula. That's the one that you need to know. Okay? You always start with that formula. And all I need is just to plug it in. You see what I'm saying? So we have the terminal voltage, that's for part A. So you just use this formula. So that's going to be 24 equals 21.2 plus 4 times R. Very trivial. Then you just solve for R. So R is going to be equal to 24 minus 21.2 over 4. And when you calculate that, I hope you are calculating things with me. That's going to be 24 minus 21.2 divided by 4. Answer 0.7. So the internal resistance, it's 0.7 ohm. There we go. Okay. Part B, he said, what is the resistance, the actual, which is basically the light bulb, that resistance across the light bulb that is shown, this big R. Well, the best way to do it is the terminal voltage is equal to what? IR, Ohm's law. You got it? Ohm's law. This is the formula for the terminal voltage. And so R is the terminal voltage over I, and the terminal voltage is 21.2 divided by I, and that's equal to 4. And then I'm going to get here 21.2 divided by 4. Answer 5.3. And there we go. Now, how do I know, because this is the last thing before I finish my lecture, how do I know that what I have done here is correct? Okay? I know it if I use this formula. In other words, look at this. What if I ask you the question, what is the total resistance in the circuit? Well, basically it is R plus big R, right? That's the total resistance. So 5.7 plus 5.3. So the total resistance here really is 6 ohm. See what I'm saying? That's the total resistance. We know that the current is what? 4 amp. Now, what is the EMF? Well, the EMF is IR, but this R is the total. You got that? Here, let's check it out and see if this is true. So if I get an EMF of 24 as given by the problem, then I am correct, which I am. As you can see, 6 times 4, and that's 24 volt, which agrees with the given EMF. Got it? Okay, so that's basically how we check. This one is a check. Okay. All right, I think I'm going to end my lecture here. Please let me know if you have any questions. And have a great week. Bye-bye.